I just wanted to give a little bit of a background to this particular award that Unidata has, put in place that honors Russell L. DeSouza. If essentially the terms of reference for the award states that this award honors individuals whose energy, expertise, and active service to the geosciences contribute in a way that is consistent with or furthers the Unidata program's mission. Honorees of this award personify the Unidata ideal of an inclusive community that promotes the sharing of data, software, and ideas through computing and networking technology. While direct involvement in the Unidata community is one avenue by which such a contribution may be made, this is not a requirement. The distinguishing ethos of awardees is their contribution and dedication to accessible and reproducible science and education in the geosciences. And I always say Unidata literally used to have a bumper sticker called, that said community driven. And literally from day one of Unidata, the program has been driven by the community and governed by the community. And as such, we thought it would be apt to, establish an award that honors individuals. Just a little bit of a background on who Russell L. DeSouza was. He became active in Unidata in 1989 as a member of the Users Committee, and I had a distinct honor of joining him on the committee because that committee was established that particular day when Russ and I met here in Boulder. I was also one of the inaugural members of the Unidata Users Committee back in 1989. And it is after Russell L. DeSouza that this award is named. And Russ, he was not only a member of the Users Committee, but he did a lot of great work to further the community cause. In particular, back then, we had to make decisions on where to place the satellite imagery because we didn't have the bandwidth to collect full, image or even full CONUS image to distribute to universities through a different satellite link by which universities were receiving data. So somebody had to make a call on where to place the centroid for that satellite imagery based on the weather of the day. And Russ and his students in his lab took on the responsibility and fulfilled that role for many years. And it was that kind of a contribution he always made to the program where he took on responsibilities as an adjunct to programs' goals. And Russ was a faculty member at Millersville University in Pennsylvania, which is now very well known in the field. But when Unidata was created, people are asking, where is Millersville University? And here is a proud graduate of Millersville University, Scott Jacobs, sitting here in this room. Now it is one of the flagship, universities in our field. And a lot of that work got started because of Russ's involvement in the Unidata program, where he brought a lot of Unidata tools and real-time data into the classroom. And as they say, the rest is history. So it is, and then he graduated or moved on to the Unidata Policy Committee. That is the name before the Strategic Advisory Committee name change occurred around 10, 11 years ago. And after a couple of years on the policy committee, he, had melanoma, and soon after, he passed away. And in his honor, Unidata created this community-facing award and essentially charged the users committee to come up with names in the community and go through a selection process to identify the individuals And without any hesitation, I can say that Ryan personifies, the goals of this particular award and the spirit that Russ DeSouza and many others since his time have brought to enhance the community on behalf of the program center and the program as a whole. So congratulations, Ryan. With that, I'm going to turn it over to Kevin to read the actual citation and introduce you to give your talk.
Yep, it is great to be with everybody today and to honor Dr. Ryan Abernathey, who is an associate professor in the Department of Earth and Environmental Sciences at Columbia University's Lamont Doherty Earth Observatory, and as of this meeting, a member of the Unidata's Strategic Advisory Committee. While members of Unidata's governing committee are generally not considered as candidates for the DeSouza Award during their committee tenure, the Users Committee selected Ryan before he joined the SAC. We're fortunate to have him here both as a committee member and a DeSouza honoree. Ryan is the principal investigator for the Lamont Doherty Earth Observatory Ocean Transport Group, whose mission is to, quote, advance scientific understanding of how stuff moves around the ocean and how this transport influences Earth's large-scale climate and ecosystems. He may be more familiar to those of us involved with MetPy project and Unidata's other Python activities as one of the principal collaborators on the PanGeo project, which is a community gathered to develop software and infrastructure to enable big data geoscience research. His community work, which we are recognizing in a small way with this award, emphasizes the importance of open data, open source software, and the overall reproducibility of research efforts, concerns that are also at the heart of Unidata's own programs. Since Ryan couldn't be with us in Boulder for this meeting, we've already mailed him his physical plaque, but I do have a copy here. Folks want to see it here. But we wanted to tell you what the plaque reads, and it reads in the following text. For your dedication, enthusiasm, and inspiration that truly reflect the goals and ideals of the Unidata program, we present Ryan Abernathey with the 2022 Russell L. DeSouza Award. You exemplify these ideals through your ongoing advocacy and efforts promoting the open availability of data and software in the geoscience community. We value your contributions to a variety of community-supported software packages, and especially commend your work to improve data literacy and help the community make efficient use of big data. We offer this award in recognition of and appreciation for your many years of outstanding service to the geoscience community. Join me in congratulating Ryan Abernathey, our 2022 Russell L. DeSouza Award winner.
Okay, so yeah, I've decided to prepare a sort of provocative talk that will sort of dig into, I think, some of the big challenges and questions facing our community. Just to start, wanted to start by just really thanking Unidata and this committee for this award. I read up on Russell DeSouza and I have to say I really feel a huge amount of personal alignment with the ideals behind this award. I would say that these are now sort of my main focus of my career, to the detriment of my oceanography research, particularly the ideas around sharing of data and software and accessibility and reproducibility. I guess I'd like to try and inject a little bit of urgency into this meeting and this community and to Unidata as a whole. A sense of urgency that I felt a little bit, but I think needs to always be emphasized here. The past few years have made it clear that climate change is really here. We are facing the impacts. Weather and climate data have never been more important to our species and our planet. And at the same time, the data about the planet are exploding in volume. So here's just a chart from NASA about their growth in their data archives, and I'm sure you can make a similar one for every space agency and data program, and not to mention all of the private companies entering that space. So we've really got some trend lines that we're confronting on several levels. Another big thing that's changed in our field since I was in grad school is just how big the private sector interest is in our data and our tools and this problem space in general. Last year, $90 billion were invested in what's broadly considered climate tech. It spans a lot of different things, but certainly includes climate adaptation work. We just got the Inflation Reduction Act, which is a massive injection into this whole space. And I think we should all be thinking hard about what's our engagement with this growing private sector going to look like. And to get really specific, one thing I've learned over the past few years is that reselling open data is a viable business model. There are several companies out there whose whole business is to extract data from free and open data archives, package it in a more user-friendly way, and resell it to people who are willing to pay for the convenience of having it nicely cleaned and organized and put behind some convenient API. On one hand, I support these companies to innovate and make money however they can. On the other hand, I feel like to some degree this indicates some level of failure at the level of the public sector, that these services need to exist. So combining this with the first slide, the sense of urgency, I think our community, we're working on one of the most important problems in the world. We also have a lot of work to do to realize this potential of data access. So for me, it comes down to this idea of open science. This is sort of the motivating principle behind all of the work I do in this space. And I believe what many of you in the audience do as well. So there's a lot of different flavors of open science, and what does it exactly mean? I sort of tried to put it into like pseudocode. We really want to allow everyone in the world access to verify and extend all scientific knowledge, directly. Or we want to allow any people in the world, any groups in the world, to collaborate and generate new knowledge or new applications of scientific data. Right? This would really transform the world, and I believe it would put us a long way towards the goal of responding to the climate crisis. And so I'd like to think about the work we do in terms of lowering the barriers to realizing this vision. There are many, many barriers to this. Most of them are political, social, economic, and those are much harder problems than I can hope to solve. So I'll be focusing mostly on the technological barriers to this open science vision. So now for the provocative part and the title. Fair data has become all the rage recently. I see this acronym everywhere, and of course I love it. Sounds great. Findable, accessible, interoperable, reusable. I don't think you'll find a single person who disagrees about the idea that data should be fair. But for data-intensive scientific workflows, fair is a lot easier said than done. It's not quite specific enough about what exact protocols, technologies, or infrastructure we should be using. So fair is more of a value system, but it's not a platform. And I think the challenge for those of us working in the technical space is to think about, what should that platform be? I want to distinguish a little bit between different types of workflows that we see in our field. And I'm going to use this term data-intensive science a lot. That's where I'm focused. A lot of us also do simulation. And I think, to some degree, these are coupled, but it's useful, I think, to put them in separate categories. Often with simulation, we're starting from something relatively small or simple, like, the Navier-Stokes equations. And we put those through a computer, and it spits out a bunch of numbers, spits out a bunch of data. Whereas data-intensive science is more the reverse process. We start with a bunch of data, and we're actually trying to get some insights or make some predictions and guide some decision-making, something like that. And I think these are quite different workflows in many cases. Simulation is kind of a known computational problem in many cases. We've been thinking about how to solve, the the Navier-Stokes equations for a long time. We have a lot of scalable algorithms for that, and we have an architecture in an infrastructure that is really good at running big models, right? We know exactly what that infrastructure needs to look like. Data-intensive science is much more open-ended. It's exploratory. We don't know exactly what we're looking for at the end. There's a human there in the loop. This is where a lot of AI and ML work is happening. There's generally a visualization component. We want to look at the data, and in general, this is just a highly varied computational pattern and algorithm, and there's no real standard architecture or infrastructure for how to do data-intensive science. And I think this is where a lot of the questions are today. My claim is that open science, and in particularly data-intensive open science, needs some kind of platform. What do I mean by platform? Well, first I want to acknowledge that that word platform itself is incredibly overloaded. Everything is a platform these days, but it's useful to look up what the definition actually is. Platform is something you can build on, right? So for an open science platform, we need something we can build scientific discoveries on or applications. And if you have access to the platform, then you can run those applications. So a great example of a platform is the Apple iOS App Store. If you build an app for the App Store, everyone who has an iOS device can run it. Or if you put your ads on Facebook, everyone in the world can see them. Everyone who has access to Facebook. So those are platforms. And if we had something like that for open science, it would push things forward a lot in terms of reproducibility and collaboration. A lot of us are excited about cloud, clearly, but at the same time, it's also clear that cloud by itself is not an open science platform. It's more like a potential infrastructure for such a platform, but it's not itself the open science platform. And I think this gets confused in a lot of discussions about open science. There's this sort of very quick reflex to say, open science, cloud, yes, we'll be in cloud, then we'll be open. We'll be doing open science because we're in the cloud. It's definitely not the case. And this is a place where we need to do a lot of strategic thinking. At the same time, the cloud can be very important for that. And as a final sort of provocative question that I'll return to, does this hypothetical open science platform itself need to be open or open source? Okay, so I'm going to have to accelerate because we started a little late, but I'm going to try and churn through this overall outline. That was the introduction. Sorry. Here's some things I want to talk about, and I want to start by giving you my assessment of what I think the status quo of data-intensive scientific infrastructure is. I'm going to talk about our experience with Pangeo and cloud computing. And then I'm going to talk about where I think we need to be going next, which is moving from software to software as a service. And then I'll sort of conclude with some open-ended sort of rambling about what the future may be like, and even added a slide on what Unidata's role might be or how to ask the question. Okay, so this is what I think our infrastructure is today for most scientists. Let's say 95% of scientists don't use anything outside of this, but by outside I mean cloud, right? So just about everyone's got a laptop at this point. A lot of groups have some server in the closet. Maybe your department has got a cluster where you can run, Wharf or ROMs or something like that. And then if you've got the right sort of grant, you can get access to an agency supercomputer, NCAR supercomputer, or something like that. It's really interesting to me that as you move across this spectrum, you get more resources, but you also get way more security and more constraints on what you're allowed to do. To the point where when you get onto that agency supercomputer, you're probably not even on the internet anymore. And I think this is, this really kind of, when you're trying to build tools for everybody, this provides some really strong constraints. What can we really rely on? What can we assume people have access to? Unix operating system, some sort of file system. They can run code, in Python or R or Fortran, and they can, run commands in a terminal. That's about it. That's about the only sort of infrastructure we can assume that everyone has access to. And the use of high-level data services, APIs, things like that. I don't know, as like a university scientist, like I don't know anyone who does any of that. Like using like an OGC API to do data access, just unheard of in my world. So what we have is the download model. This is how we were trained to do science. This is how I was trained to do science. You get your files, you download them to your laptop, and then you analyze them. And that's just fine when you're in megabyte territory. It's probably fine when you're in gigabyte territory. It starts to get pretty painful when you're in terabyte territory. And once you hit this sort of petabyte scale, it's clear that this is never going to work, and that's not feasible. And for a lot of the applications that I'm interested in physical oceanography, we're starting to, we're definitely in the terabyte stage, and we're getting towards that petabyte stage. So this problem is real. The way most of our institutions have been solving this is to create a data fortress. This is a term that was coined by Shel Genteman, which I think is pretty interesting. So what's a data fortress? So I'm at a sort of rich Ivy League university up here on the hill. And so we get a bunch of data from all of our favorite data providers, and we stick it on our cluster in our basement. And now we've got a great sort of data fortress for the people in our group. And we can do some nice science with this. We can analyze our data. And then we want to try and share our project so we can be fair. And the very first line of our code is opening up some files on this inside this data fortress that you, the person who found my code on GitHub, don't have access to. This is actually even just beyond trying to share your results with the world. My university has this wonderful policy where they immediately cut off access to our supercomputer for any employee the moment they leave Columbia. So if you have a PhD student who's trying to finish their paper after they've gone to their postdoc, forget about it. They're cut off. So this is kind of, I feel like, brings out some of the key problems with the status quo, right? So just kind of go through this list of the complaints. I think our emphasis on files as a medium of data exchange in general is not right. It creates a lot of toil for scientists, downloading, organizing, and these file-based data sets are kind of a mess. Files are not the only way to share data. The work of this data wrangling that we have to do do data-intensive science is very rarely collaborative. You may go through have a postdoc spending months to download files and clean them and organize them so they're ready to be analyzed. And that's just one-time work. That effort can't be shared. You can't really write a paper about it. You can't even really put the code up and have it be useful or interesting. So it's just kind of burned effort. It's expensive, right? So you either need your own cluster, your own, or you need access to a big agency supercomputer. And this is really limiting participation. A lot of folks in precisely the communities we're trying to engage with more these days in science, historically underrepresented groups and institutions and countries are really left out. The fact that our data are in this data fortress really limits access to outsiders, and that is a feature, not a bug. Our IT department is very proud of the fact that no one can get in to access our cluster. They consider that a real achievement, but it's diametrically opposed to the goals of collaboration and reproducibility. And then finally, in my experience, each of these fortresses is a special snowflake. You can write code that will run on one supercomputer, but it's probably not going to run on another supercomputer without significant modification. Okay, so that was complaining about where things are at. Now I'm going to talk about why I'm optimistic about cloud computing and what I think we have and have not been able to accomplish with the Pangeo project. So the cloud sort of offers an alternative architecture to the data fortress model. Here I use the term from Fernando Perez, the creator of Jupyter. Cloud offers the possibility of creating a data watering hole where everyone can come together around the same data sets and collaborate, share data, share ideas, share code in a much more fluid and frictionless way than our status quo architecture. When a lot of us think about what cloud computing might look like, I think a lot of people think about Google Earth Engine. I think it's a really impactful product in this space that has really kind of was the first cloud scale analytics platform aimed specifically at the geoscience community, really, geospatial more accurately, kind of GIS workflows. And that's an example of a vertically integrated platform. They've got all the data, all the compute. You just log in and you do all your work there, and you get back out your figure or whatever. And I think this really kind of has set the standard for what people think about and expect from cloud computing. And there's other examples of platforms like this. Descartes Labs platform. I'm not sure that if this is a sustainable model, to be honest. Google Earth Engine doesn't have to be a sustainable product. It's subsidized by Google. It's not like a product like Google Docs is. It's more of a community service they run. Descartes Labs tried building a platform like this as a venture-backed company, and it hasn't really worked out the way they expected. And there's some interesting articles from the founder online if you're interested in reading up about why not. But it's very expensive to run this sort of thing. So you have to sit on 50 petabytes of data, and that bill is pretty large. This is what I consider option B, a very messy slide. That sort of a beautiful mess of interoperable cloud-native data, software, and services, right? So this is the sort of future I want to live in, where we've got analysis-ready, cloud-optimized data out there somewhere in the cloud, and we can all bring whatever sort of computing framework we want right next to it, and we can run this anywhere. It's not specific to Amazon's cloud or anything like that. So this is a bit messier, but I think ultimately more sustainable and scalable architecture for science. This is the sort of thing we've been trying to build in the cloud with Pangeo, and a lot of lessons learned. And let me just say a little bit about what Pangeo is. Pangeo is really a community that has been iterating together on data-intensive workflows for about 5 years now. We're all starting from scientific users and use cases who are bringing the questions, and in many cases, the developers and the scientists are the same people. But really identifying like where are the bottlenecks in our infrastructure. So for me, it was I had 100 terabytes of ocean model output to analyze. I just couldn't do it on my local server anymore. I needed a scale out architecture in order to make the plot I needed to make. Then we've done a lot of work on open source software libraries for data analytics, right? So we contribute very widely to the open source scientific Python ecosystem, but I guess our home is probably the Xarray package, which I work on a lot, which is kind of at the nexus of a lot of the sort of architecture diagram. And then we deploy this stuff wherever we can, right? So we've run this sort of software stack on all the HPC systems, NCAR systems. We've put it in all of the major clouds. We've ran it on Jetstream. It's really not that specific. And in sort of iterating and going through this cycle over and over, I think we've made some real overall improvements to the workflows and the technology, even though it's hard to cite like one exact specific thing. But I definitely feel that we've had an impact here, and that the software ecosystem is much more powerful and effective than it was 5 years ago. I think it's interesting to tell the story of how Pangeo got into cloud. It was an accident. So this is our first proposal to the NSF. And you can see they want to fund us, but they wanted us to cut 18% from our budget. And so they asked us how we would like to do that. And so, of course, we said, oh, yes, we'll take the funding, we'll make the cut. And what we did was we cut all the servers we were going to buy. We had this plan, we were going to buy a bunch of servers, because that's what you do in a proposal budget, right? And we said, instead, why don't you give us some of these cloud computing credits that you're handing out? And they bought it, and we got $100,000 worth of cloud computing credits in Google Cloud, and that allowed us to just figure a bunch of stuff out without a lot of pressure. So our cloud native stack in Pangeo looks something like this. We are very enthusiastic about Zara as a storage format, and I could put NetCDF there now because Zara and NetCDF have been united as one format. And that's really important in cloud because it plays very well with object storage, like Amazon S3, which is the sort of most cost-effective and performant way to store data in the cloud. We use a parallel computing framework called Dask to help us scale out our processing so that we can take advantage of all those nodes available on demand in the cloud. And then we interact with that stuff through Xarray, which is sort of high-level API for data analysis, very much inspired and based on the NetCDF data model. And then there can be a lot of other domain-specific packages that come in here and interface with this. Should have put MetPy on there. Definitely want to acknowledge MetPy. It's an important part of this ecosystem as well, and interoperable through this whole stack. We're excited about the cloud because it's really fast if you do it right. So here's a paper we wrote from a year or two ago where we really sort of benchmarked, okay, how fast can we chew through data using this architecture? And we found, with fairly modest levels of parallelism, say 40, 50 processes going, we can process data in the cloud at a rate approaching 10 gigabytes per second, which is really fast. At that speed, you can start thinking about processing petabytes of data and doing that type of science. And so this is just sort of evidence that I think this analysis-ready cloud-optimized data is an important piece of the picture. So we're trying to push this acronym ARCO data to describe the sort of data sets we want to see. And it's hard in Pangeo to sort of point directly to impacts because we're kind of contributing very broadly in a lot of different ways and sort of just plugging all these pieces together that already existed. But there's a lot of anecdotal evidence that this stuff has been having an impact from individual users who just have told us how this Pangeo technology and approach has really sped up their workflows. And then we see, large organizations and agencies who are adopting this technology. So Microsoft's Planetary Computer is really, the architecture is largely inspired by the Pangeo model. And, European Space Agency, for example, has invested quite a bit in sort of Pangeo-based data cube technologies for working with data. So just a few examples. So let me talk about where I think we've seen the limitations of the Pangeo approach. So I said earlier that science needs a platform, and sometimes we describe Pangeo as a platform, but I think that's wrong. At least the way we're deploying it today. Pangeo platform is kind of understood to be a Jupyter hub in the cloud with Xarray and Dask connected to some data in the cloud, and the issue that I see is there's a lot of different versions of that out there. So, Unidata has got their Jupyter hub on Jetstream, and, NASA's got a few Jupyter hubs, and then we run these Jupyter hubs, and, the Microsoft Planetary Computer, and it's as if there was, 50 different app stores, for iOS, and it's hasn't quite congealed into a platform. There's a lot of cool prototypes out there, but we don't have that sort of global interoperability that we need for reproducibility. There's a lot of work involved in trying to deploy this architecture. in the cloud. There's no sort of Pangeo as a service. You need some people who are willing to wade into Kubernetes and Terraform and do cloud-like things, and those people are in pretty short supply. That doesn't really scale. And then, getting data into the cloud in Arco format is quite hard, full of toil, and very inefficient today. Just speaking more generally about cloud, I was part of a NSF report in 2018 about enabling computer and information science and engineering research and education in the cloud. And we noted some of these structural reasons that are making it hard to adopt cloud. Overhead policies, purchasing challenges, IT support, just the technical complexity. And I feel like none of this has really changed in 5 years. It's still very hard for academic scientists to get access to cloud computing, and let alone use it effectively. So there's great potential there, but I don't think it's solved by any means. Okay, so try to go fast here. Where do I think we need to go? I think we need to go from just developing software to providing software as a service. Okay, and the reason I think that is that in order to really democratize access to scientific data, we need solutions that scale. Most of what I see happening in this space is sort of consulting style project work. Oh yeah, this community wants a Jupyter hub in the cloud. We'll stand that up for you. We'll get some engineers on it, and we'll work with you. This is rate limited by the number of engineers out there to do that work. Completely different delivery model is software as a service, where the same product can be sold to many customers with a low marginal cost and anyone can buy it. That's why venture capital loves to support SaaS businesses. If we think about what are our most impactful open science tools today, probably at the top of the list is GitHub for me. Google Docs. Think about how we work today. That would have been impossible without Google Docs. Overleaf is a great one. Zoom, are we using Zoom now? I forget. But the point is, these are all proprietary SaaS applications. They may use open standards, but they're not open source. And they're essential for open and collaborative science. And we find some way to pay for them. There does exist an ecosystem of software as a service around data and data analytics. This has largely emerged in the past 5 years, and it's called the modern data stack. The modern data stack is an ecosystem of interoperable products that in many cases use open standards to interoperate, centered around a data lake or data warehouse, right? So probably one of the most well-known companies in the space is Databricks. We have technologies like Snowflake or Google BigQuery. There's a whole bunch of services you can buy that plug into this stuff to do things like data ingestion, transformations, building dashboards, AI and ML operations. This is what all the companies doing enterprise data science pretty much use. No one in science, as far as I know, touches any of this. But it's a very interesting model for how software could be, delivered to data-intensive applications. I'll note that, I think before this existed, a lot of companies face the same challenges that we are all talking about. Oh, how do we deploy stuff in the cloud? It's too complicated. How should we set it up? We don't have enough DevOps engineers, and so this sort of arose in response to that. So to answer the question of how can we deliver an open science platform in a scalable, sustainable way, I see two different paths forward. One is to just embrace this idea of commercial software as a service, a modern data stack for science. The other is to cultivate community-operated software as a service. And a great example there is Wikipedia. Right? Wikipedia is one of the best and most valuable websites on the internet. And it's not a commercial product, it's a community operated endeavor. It is a very complex community operated endeavor. Another example, probably closer to home, is Conda Forge. Conda Forge is more than just software. It's an actual service that delivers and builds software packages for us. Binder is a great example. The 2I2C Jupyter Hubs is a great example. So my feeling is we probably need a mix of both, and I am exploring both. I'm going to tell you very quickly about two explorations we're making in this space. One is this project we call PangeoForge, which is a community-operated SaaS for extraction, transformation, and loading of analysis-ready cloud-optimized data. And the other is a company that we just started called EarthMover, which is building a cloud data lake platform oriented towards scientific data. So with PangeoForge, the problem that we're facing is that making this analysis-ready cloud-optimized data is really hard. Getting data from its archival format, say in a NOAA server or on your cluster somewhere, into the cloud in, say, a ZAR format, is a lot of work and takes a lot of specialized knowledge that very few people actually have. So the goal with PangeoForge is sort of democratize the production of ARCO data, so that really minimum, just basic understanding of how to find data, where the data exists, and how they should be processed is all that's needed to get data into the cloud. We're directly inspired by Conda Forge, which has sort of done the same thing for packaging of software, particularly software with complex binary dependencies. Conda Forge has now got over 15,000 packages and close to 4,000 contributors. I think it's a really shining example of the community-driven infrastructure. So the PangeoForge project, funded by NSF, contains two main parts. One is just an open source Python package for creating these data pipelines, recipes, which can be used in standalone mode to just ship data around however you want. And then the other component is PangeoForge Cloud, which is a sort of cloud-based runtime for those recipes, which integrates with GitHub. And exactly like Conda Forge, sort of follows what's happening in the GitHub repo, translates that into actions. We use our sort of back end, we call it Bakery, which then sort of responds to events in these repositories and downloads and moves data around and stages it into the cloud. So the vision here is that we can have sort of collaborative data curation happening openly in GitHub, the same way we work on open source software. We want to work on open data this way. I'm really excited about this vision, and we're starting to see it take shape, right? So PangeoForge Cloud is live. It's open for business. You can go check it out. There's data up. The data are being stored in open storage network right now, so outside of the commercial cloud, in sort of more of the government-sponsored cloud, if you like. At the same time, this is super hard. This is essentially $1 million budget over 3 years, and we're doing the best we can, but we can't actually do this if only the people who are funded to work on it contribute. We need to bring in more expertise and more manpower. And so we're really trying to transition this project from something that we have sort of jump-started to a community-driven project. And there's some indication that that's happening. There's a lot of interest at NASA in using this tool. And I'm really excited about it. Now, another thing that I'm trying much more recently, new direction, is that we've decided to start a venture-backed startup. Our company is called EarthMover. It's a public benefit corporation whose mission is to empower people to use scientific data to solve humanity's greatest challenges. And the thinking here is that this is the model through which most of the really effective and transformational data-intensive software as a service in the cloud has been developed. And we see a clear need for this type of product in our space. And so we're trying to build that and provide it as on a subscription basis. And so what we're building is a product called Array Lake, which is supposed to be a high-performance foundation for cloud-native analytics based fundamentally on the ZAR data model, but that can ingest and work with data from all the archival formats, NetCDF, HDF, GRIB, etc. Supporting sort of virtual data set capabilities, sort of performance optimizations happening in the background, and some extra cool features like data versioning, snapshots, time travel, governance, data catalogs, all of this stuff. So we're really sort of trying to make a product that's analogous to, say, Databricks or Snowflake's data lake, but oriented around the scientific NetCDF data model rather than tabular data. Okay, so let me try and wrap up and give you some now wild speculation about where we're headed. I think we have sort of identified what are the pillars of cloud native scientific data analytics, and what it might be like to live in this sort of cloud native future. Coming back to one of my early slides, a key principle is this idea of separation of storage and compute, right? That one provider, the provider who's providing data, doesn't necessarily have to provide compute. In my opinion, this is a sort of key architecture problem that we need to crack if we're going to actually unlock the potential of cloud. So one organization needs to be able to host the data, and another organization should be able to pay for individual users computing, working on that same data. I don't know how to do that, but if we could get there, it would be great. This is completely different from our status quo infrastructure, where one provider, one institution is hosting everything for just its own users. The open science platform isn't going to look that different from where we are now. I think Jupyter is pervasive for sharing reproducible data-intensive scientific workflows. We've got all these great scientific computing languages and computing stacks, and we've got all this great technology for storing data in the cloud in an optimized and performant way. And this can be deployed on just about any style of infrastructure that you want. The vision where I'd really like to get to is some sort of federated and extensible model wherein different organizations or entities can add capacity to this federation in a way that matches their capabilities and their missions. So, Unidata might decide we need a computing environment for these users with these capabilities. And NOAA might decide, okay, we're going to host this data, and all of it can interoperate and build on each other rather than creating more silos. And by the way, I'd like to see the traditional HPC centers in this diagram as well. Problem you start to face, though, is this idea of data gravity. Data gravity is the ability of a body of data to attract applications, services, and other data. So once you start getting hundreds of petabytes of data built up somewhere, it becomes very, very hard to move things away from it. And that is, of course, precisely what all these cloud providers are counting on when they partner with us to host petabytes of our precious scientific data for free in their open data programs. They want that data gravity to bring them lots of customers. And I think it's working. However, there's a lot of different sources of gravity, and this seems, like slightly unstable situation, right? So where are we actually heading, and is there a potential singularity in this data gravity solution? Is there going to be some sort of black hole that's going to suck us all in? Is that AWS, or can we escape? Is there some other way? I think we need a global scientific data commons that sits outside any one of the big commercial cloud providers. I think technologically it's very feasible to do this. I think that because we've been working with Open Storage Network for the past few years, they have an ability to essentially host object storage, provide object storage, sitting on the cloud edge in a very cost-effective way and with very high performance. There's a lot of organizations that are very invested in decentralized data storage. ESGF is an important partner here. And then, recent scams and the latest scams and crashes notwithstanding, there's a lot of alignment with the Web3 community, which espouses the principles of decentralized architecture quite strongly. And so I think we need to be thinking about how can we get the benefits of cloud and cloud computing while keeping sort of data sovereignty, to use a term from earlier in the session. Okay, so I'm wrapping up. I just want to shout out some of the great organizations that I see working in this space and thinking hard about how to deliver the infrastructure that we need for open science. Unidata is a very important part of this ecosystem, and there are many others. And I think partnerships here are going to be key to realizing any of this. Just throw out some questions. I know we're almost out of time and people are probably eager to get going. Just repeat some of the questions I've already raised. What should teams be building themselves versus getting as a service? Do we really want each university department to deploy their own Jupyter Hub in the cloud? Is that the right model? For these services, what's the right delivery model? Do we want to have use commercial vendors, sort of co-ops? How do we avoid recreating existing silos moving into this cloud native future? Who should pay? Whose job is it to support the infrastructure for the university research community? As we said this morning, we can't expect Unidata, for example, or to shoulder the compute burden for the entire community. How can we make cloud and HPC more interoperable? And so we have more synergy between our existing infrastructure and where we think things are going. I have more questions. This is the last slide, I promise. I'm really interested in thinking about what's the unique role that only Unidata can play in our ecosystem, right? There's a lot of different players here on this page, and even more when you bring in all the companies operating in this space. But where can Unidata have a particularly unique contribution? What's going to be Unidata's relationship with the broader open source scientific software community in this world we're heading into? Does Unidata want to be a software as a service provider? This is one question I honestly have. Unidata provides software, and there's also services. There's operational services. And the delivery models of those can really vary. Is it more of a Wikipedia model? Is it more of a Globus model? Are there fees involved? I'm very curious. And then, who are the like-minded organizations that Unidata should be partnering with so we can all go forward faster together? So I know that's kind of a lot to swallow. I will leave it there, and hopefully we have a little bit of time for discussion.
Great, thank you so much, Ryan, for that thought-provoking presentation. A lot to chew on here. We do have a question from Chuck, so please do use the raise your hand feature. We'll work through things that way. So go ahead, Chuck.
No, Ryan, candidly, I didn't even know where to start with my questions because you hit so many things that are near and dear to my heart. Running an HPC center over at Penn State with and all that. The one thing I think your vision is always going to rely upon is, my goodness, the network is so clutch to everything you want to do. And I think what you're going to find is, as the network capabilities grow between institutions, the scale and scope of the data they can share will grow. But you're still going to be stuck with those. I love that gravity well approach to the vendors. And I don't know. I maybe it's a statement more than a question, but I think you have a interesting, challenging, intractable problem depending on how big the data sets are. Because everybody's got to pay for something. I don't know. What's your philosophy on that? I mean, how are you going to approach that?
I think Pangeo, we've had the unique opportunity to sort of be in the middle of this discussion between cloud providers, and we have quite close relationships with, say, like the AWS public data program and like agencies like NASA. And the thing about the cloud providers is they don't actually really want to even own the data. Like, they're doing all of these public data programs, but they're really struggling to find people to actually manage they'll give away storage, but they're not going to run the pipeline, right? And so my strong feeling is that we need a new relationship with the cloud providers around public data. One organization that I think is doing really interesting stuff in this space is Radiant Earth. They run the service called ML Hub, focused on sort of geospatial machine learning data training. The new executive director there is Jed Sunwell, who used to direct the open data program at AWS. And so, yeah, I don't have an answer for you, but I think we need to, rather than just sort of taking what's handed to us by the cloud providers, we need as a community to be much more active and unified in asking for what we want, negotiating with the sort of combined, like as a unit, as a field with the cloud providers and sort of setting the terms. And that can include things like you can negotiate like network egress waivers. Like everyone complains, well, if it's in the cloud, I have to pay egress fees. Well, not if you negotiate that away. Like that's all negotiable, right? It's just a question of getting leverage in that negotiation, which an individual small college does not have, but like the entire weather and climate research community does have.
Well, with one last comment, I'll pass the baton, but I would almost suggest that we need to almost have the equivalent of a UCAR for cloud data at this point and compute data out there. So places where these non-commercial entities can get together and figure out how they're going to work together to make these things happen. It's happened before, it can happen again. So,
Eric?
Yeah, I'm not on mine. I'm not on mine, but I'll go after Eric.
Okay.
Yeah, great talk, Ryan. Really neat to see all that pulled together. And you're dealing with some very big picture questions there, obviously. And so I wanted to kind of maybe reach back into history and get your take on this. You mentioned some of these universal values of openness and fair, and very universal values that we might expect to have had a role in supporting scientific progress in the past. There's been previous eras of rapid scientific advancement that I would suspect are underpinned by some of those same values. And so in the communities that you're in and visiting, are there any sort of historical analogs that you look to about how to sort of organize this shared society-wide knowledge sharing activity?
I think ESGF has been a great, really great organization for data sharing infrastructure. I mean, it's, I think, probably the de facto, most, they've had the by far the biggest impact, and they have a lot of funding. And, like in many analogous ways to Unidata, there's a lot of, and I don't mean this pejoratively, but there's a lot of legacy infrastructure to ESGF, right? They're maintaining a software system that was created pre-cloud, right? And so I would like to think that ESGF can transition to playing that role, because it's already exists. It's already got everyone at the table. It's got all the big agencies, and it's focused on Earth system data, which that was the same scope that I heard mentioned for Unidata, right? I think it would be foolish to throw that away and create a new organization. On the other hand, I'm not certain that ESGF has the flexibility to adapt to what's needed. The ESGF leadership is very, this is being recorded. Okay, I gotta watch what I say. It's undeniable that ESGF in the US is run by the DOE. My view is DOE's infrastructure is so impressive and so effective for DOE scientists that it can be easy for them to lose sight of people who are not privileged to be in that enclave, right? And so I worry that that's one concern. We really need to think about how are we reaching those minority serving institutions? How are we reaching those communities with low internet connectivity? Like really getting everyone included.
Yeah, and maybe to save you from having to put your foot in a sort of current moment issue, my question was really getting at looking back into history. I saw Victor just mentioned paradigm shifts, like really actually looking back at history and what has worked well that allowed, say, chemistry to advance, and like what did shared infrastructure look like in that broader perspective. And that gets us a little bit out of the mindset of the current computery moment towards a little bit maybe more universal human things.
Sure. Okay. I'll just respond quickly. I think the big paradigm shift that's happening right now is what I started my talk with. The private sector interest and involvement in this data is exploding. It's increasing by orders of magnitude. I'm seeing it now. All of a sudden, our students have all these new job opportunities at all these companies. Every one of those logos on my screen, like no one's buying servers. They're all in the cloud. right? And so even if the universities are not moving to the cloud, all the employers where our students are going to be working after they graduate are in the cloud. And that's, I think, going to drive changes more than anything we do in a top-down way.
Yeah, so thank you, Ryan. That was I hope this was recorded and something we can reference in the future.
Yes,
or I hope that you get, actually, I'm coming in as the IT and I chair at ESIP, and I wonder if you'd come and give that talk to that group, because it fantastic. Anyway, your point about kind of building a consortium of edge data providers, I think is well crafted. And I want to reflect a little bit on your question of what can Unidata uniquely do here. And I think Unidata could lead the consortium of edge providers as kind of an architectural visionary, right? And I guess I wonder if you see a natural architecture for that forming, especially thinking about, you've got for-profit interests that are going to be pulling from that. You've got non-for-profit, you've got academic, you've got government. Everybody's going to have an interest in that thing. Everybody's going to have performance expectations. Like, it's going to break. How? I guess, do you have any thoughts about like the governance of that edge storage system and how that might unfold?
Yeah, it's a great question. It's really exciting to think about. I think, like, what would it look like if we built a purpose-built data facility for all the science, like say NSF level, right? They're not building another supercomputer, they're building the data. There's a big group who's working on this sort of stuff, and they're, Globus, Lumiere, Open Storage Network Group is closely affiliated with them. There's a group at University of Utah led by Valerio Pascucci, who has this national data fabric thing. So we would definitely want to link up with them. But yeah, I think the challenge would be to create an organization that, because technologically we can build object storage, but on a service level, can we deliver an experience that's competitive with commercial cloud? I think that's interesting to think about. I think it will require an organization that's a lot more dynamic than a lot of our existing, computing centers. That is much more service oriented, much more sort of customer oriented. That's really trying to build something that say that satisfies SLAs, right? Like things people expect. And can it? It's a hard problem, but I think there's a huge amount of investment happening in NSF around data infrastructure. There's we're at a good place right now in terms of federal funding. So this is an ambitious thing, but I think it can be done with the right leadership and with the right vision. So yeah, kind of punting, but I'm optimistic.
Yeah, good.
Any other questions for Ryan or discussion on his questions? I think one of the things from my end is at a smaller institution, we happen to be a Google campus. I'm surprised there hasn't been more maybe effort from organizations like a Google or Microsoft to make easier inroads, because we're already in the Google Drive environment, right? There's not a similar way for the ease into the cloud that is just then adding on to that for service type thing. And that, I can see a real easy buy-in for institutions since we're already into that realm, but then just making that some sort of front end piece that then allows that accessibility would be a really interesting way to get more institutions, especially institutions that otherwise don't have the resources to build our own data fortresses, right? To potentially capitalize on some things that then all those students then potentially get that in whatever next iteration thing they are at, because that's what they have the experience in. So there's a buying part there. But anyway, more of a comment than a question. But Thomas.
One thing I've sort of struggled with some of the ed comments thrown around this conference or workshop is a lot of students don't know like file systems. I've dealt with this when I taught data science at Mines, like folder structure or even just basic Unix commands, and so it's like kind of balancing that sort of ed compared to the future is everything's going to be one massive Jupyter hub hosted by someone. And so, as time sort of marches on, at least in my space, It is easier and easier and easier to train, serve, and deploy machine learning models than it was even a couple years ago. And it's like, if we think about what this might look like 5 years from now, let's make sure that our ed and training reflects those true skills, which might look different than even skills today. Well, I don't know, Ryan, if you have comments on, terminal commands will forever be useful. I'm not trying to say that we should never, teach those things, but like if you stuck a student only in a Jupyter Hub, is that too limiting, or is that fine?
I think a Jupyter Hub is too limiting. Like just Jupyter Hub alone is not solving our data democratization challenges. I think what is clear is that like technology will go forward, right? Like all of the trends are that like I don't want my son to like have to learn how to manage like files in a directory. Like I don't want him to learn how to like do VHS tapes either. Like Netflix is much easier. Like, and I think this is a one-way street. But I think we're still very early in what cloud native science looks like, right? Like there's a lot that still needs to be built. It's not like Jupyter in the cloud is not the end game. So like you should be thinking about like what is the thing that like what is the most painful part of my workflow? What is holding the most people back? And then go build like the solution to that. Like,
and I think to couple on to Thomas's comments about where the education goes, I think for a lot of people in this room, the one thing that we can't lose in all of this is training the trainer, because that, you have 30-year time horizons for faculty members, and if we don't dedicate and think about that as its own strategic element to then train the students, otherwise then it's only the most recent then like PhD graduates then are who are ready to do that. That I think it's going to be a severe limitation for allowing the more fast and nimble adaptation that we desire and that is needed to solve these problems that we face.
One thing I agree, but the caveat is I don't know what to teach people about cloud. I teach a class in data analysis with Python, and like I still don't know what to teach them with cloud, because like it's going to be like it's changing so fast, it's so unstable. Like so before we can develop a curriculum, we really need to we need to improve the technology as well, especially the part that users see.
Yep.
I mean,
Eric,
yeah.
last comment.
It's a good one. In the last 10 years of my career, I would say it's actually been remarkable how much the Jupyter Hub and the notebook model has become the default thing that students came in with. And somehow they totally skipped file systems and how NumPy works along the way. And they're just doing stuff in notebooks in a way that is a real testament to the success of that platform. And I guess that maybe gives me some hope that we have made, at least in advance, there as a component of how we get the users to hop into the lake, so to speak.
Ooh, I like that data lake metaphor.
Jump into the lake.
All right. Any other last comment from Ryan or anybody else in the group?
Notebook is a fuzzy blanket for the students. BI is not.
Yeah. All right. Well,
I see Notebook as replacing Excel, right? It's not replacing well-crafted software. It's a step from people who are not coding at all to start doing some code. So,
but one day notebooks will work with Git. I know.
All right, let's thank Ryan one more time.